We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
I feel the liftoff. The clock has started.
This is a new and strange environment at first. Just suddenly finding yourself in orbit.
Okay, I'm separating from the spacecraft. Getting my feet out. Okay, I'm out. Really looks funny out there in my glove out there, Jim.
Jimmy 4, get back in.
Okay.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you're listening to episode 47 of the Space Rocket History Podcast. And now, Gemini Concepts. Many aspects of modern spaceflight were first suggested in the space travel writings of the early 20th century. One aspect was the value of rendezvous in orbit. It first emerged as part of the space station concept, which can be traced through the works of Russian pioneers of astronomics Tsiolkovsky, Kondratyuk, Tassander, and in the writings of their Central European counterparts, Hermann Oberth, Walter Hoffmann, Guido von Pirquet, and Hermann Nordung. Their goal was flight to the moon and the planets, but their calculations suggested that chemically propelled rockets might lack the power to launch such journeys directly from Earth's surface. If a journey were carried out in stages, however, the problem might be surmounted. They proposed using a space station, a stopover point in orbit. Once such a station was built, any number of rockets might be launched to meet it, each bearing its cargo or fuel or supplies to be transferred to the station. When enough had been gathered, fuel and supplies might then be loaded aboard an interplanetary vessel, perhaps itself constructed in orbit, and the real journey to the planets could begin. In effect, the trip would be launched from orbit. The greater part of the velocity needed to escape Earth's gravitational field had already been attained. This concept had been widely accepted in space travel circles by 1929. While rendezvous was clearly a key technique in the scheme, it failed to receive any special emphasis. That changed after 1949, when two members of the British Interplanetary Society pointed out that orbital staging need not depend on first building a space station. The pieces of an interplanetary vessel might simply be assembled in Earth orbit without troubling to construct a space station. Or several rockets might meet in orbit and transfer their fuel to one of their number, which would then embark on the final mission. The rapid spread of this idea brought rendezvous into sharp focus. The first paper specifically addressed to the problem of establishing contact between orbiting vehicles appeared in 1951. One result was a renewed attention to orbital mechanics, a topic that had languished since the path-breaking work of Hoffmann in 1925. By the end of the 1950s, a theoretical framework for rendezvous techniques had largely been established. This brings us to Project Gemini. Gemini took shape after Apollo had begun, in part to answer a crucial question for Apollo. Was rendezvous and docking in orbit a feasible basis for a manned lunar landing mission? When NASA officials appeared before Congress early in 1962 to justify the new Gemini program, the heart of the case, they argued, was the need to develop and prove the techniques of orbital rendezvous. Project Gemini was intended to show that a piloted spacecraft could meet an unmanned target in space, the orbit of the spacecraft matching that of the target so that there was no significant difference in speed and no significant distance between the two. Our study begins in January 1959, when it became abundantly clear that boosters were setting the limits of what could be done in space. This prompted NASA to its first long-range planning venture, a National Space Vehicle Program. This report surveyed existing boosters and proposed developing a series of new ones. It did no more than suggest a range of missions suited to each booster. Choosing among the possible goals now became NASA's central planning concern. In April of 1959, DeMarquise Wyatt, assistant to the Director of Spaceflight Development, testified in support of a NASA request for $3 million from Congress for research into space rendezvous techniques. He explained that the funds would be used for logistic support of a manned space laboratory, a possible post-Mercury development. However, this would depend on the resolution of certain key problems to make rendezvous practical. Among them, the establishment of referencing methods for fixing the relative positions of two vehicles in space, the development of accurate lightweight target acquisition equipment to enable the supply craft to locate the space station, the development of very accurate guidance and control systems to permit precise determination of flight paths, and the development of sources of control power. In May of 1959, the Research Steering Committee on Manned Spaceflight met for the first time. The first order of business was a manned spaceflight program to follow Mercury. Kurt Strauss of NASA Space Task Group, Langley Field, Virginia, described some preliminary Space Task Group ideas on Mercury follow-ups. These included, first, an enlarged Mercury capsule to put 2 men in orbit for 3 days. Second, a 2-man Mercury plus a large cylinder to support a 2-week mission. And third, the Mercury plus a cylinder attached by cables to a launch vehicle upper stage, the combination to be rotated to provide artificial gravity. In August of '59, the new projects panel of Space Task Group met for the first time, with Kurt Strauss in the chair. The panel was to consider problems related to atmospheric re-entry at speeds approaching escape velocity, maneuvers in the atmosphere and space, and parachute recovery for Earth landing. Alan Collette of Space Task Group's Flight Systems Division was assigned to initiate a program leading to a second-generation capsule incorporating several advances over the Mercury spacecraft. First, it would carry 3 men. Second, it would be able to maneuver in space and in the atmosphere. And third, the primary re-entry system would be designed for a water landing, but a land landing would be a secondary goal. In December of 1959, NASA released its 10-year plan. The plan said that ultimately spacecraft would carry explorers to the moon and planets, but for the 1960s, NASA chose the more modest goal of circumlunar flight, a trip to the moon, a few passes in orbit, and a return to Earth. Manned exploration of the moon and the closer planets would remain as major goals for the next decade of the 1970s. At that time, NASA planners assumed that a trip to the moon would be launched directly from Earth's surface. This would require the giant NOVA booster, the largest of the 4 new vehicles proposed in NASA's Space Vehicle Program report back in January. NOVA was a concept built on an engine, the F-1, designed to produce 6.7 meganewtons, or 1.5 million pounds of thrust. Air Force contracts with Rocketdyne had begun F-1 development in mid-1958. This was one of the military projects turned over to NASA when it was formed. 4 of these engines were planned for NOVA's first stage to provide 27 megatons, or 6 million pounds of thrust. As a comparison, the most powerful existing American booster required 3 engines to generate 1.6 meganewtons or 360,000 pounds of thrust. The belief expressed in the January report that with NOVA a manned lunar landing would be possible pervaded NASA planning through 1959 and 60. Even when rendezvous refueling or assembly in orbit were discussed as alternatives worthy of study, they were discarded as a basis for planning, since it was assumed that the NOVA approach would be followed. The choice was by no means final, but NASA was leaning strongly toward the direct ascent approach. But the question had been cited as a major one, and some of the problems involved in the all-of-the-way approach versus the assembly in orbit approach had been aired at meetings of the Research Steering Committee on Manned Spaceflight. But as NASA's 10-year plan showed, the question had yet to exert much effect on NASA's policy. Now let's jump ahead to May of 1960. Representatives of NASA's research centers, including Ames, Lewis, Marshall, and Goddard, met at Langley Research Center to present papers on current programs related to space rendezvous and to discuss possible future work on rendezvous. The meeting was designed to give the centers a chance to acquaint each other with current research and to exchange thoughts on future prospects. 3 salient facts about NASA's rendezvous research in mid-1960 were uncovered at the meeting. First, work centered on rendezvous between a space station and a ferry. Second, Langley was doing most of the work. And third, all NASA rendezvous research was in-house. NASA had yet to provide contract funds for industrial or academic studies. The problem was lack of funding caused strong resistance within NASA to any program aimed solely at the modest goal of providing a new technique or advancing the state of the art. To win funds, a research program on rendezvous needed larger ends. Everyone at the meeting was convinced that the need for rendezvous was going to become urgent within the next 5 years. What had to be done then was to find a context for rendezvous, and the best choice for that task was Marshall, since resistance to rendezvous was currently strong in both Goddard Space Flight Center and the Space Task Group. The conclusion that Marshall had both the capacity and the desire to carry through an orbital operations and rendezvous program may have been the most important byproduct of the conference. In September of 1960, Marshall's Future Projects Office was able to tell a gathering of industrial representatives that it had $3.1 million in study contracts to award during fiscal year 1961. A number of them related to rendezvous and orbital operations. By the end of the fiscal year, the office had issued $817,000 in contracts to 10 corporations and 4 universities for studies ranging from the broad problems of satellite rendezvous to the design of orbital refueling systems for Saturn. In late 1960, Marshall's commitment to the principle of orbital operations began to produce specific studies of rendezvous and orbital mechanics. As befitted a development center, Marshall's research was mission-oriented. Its role in the study of rendezvous hinged on how the technique might best be used in manned space missions, in particular, a manned landing on the moon. The focus of work at Langley also shifted to a novel application of rendezvous technique, rendezvous in lunar orbit. The essence of the idea was to leave that part of the equipment and fuel needed for the return to Earth in lunar orbit, while only a small landing craft descended to the lunar surface, later to rejoin the orbiting mothership before starting the trip home. In one form or another, this idea had appeared in the work of Oberth, Kondratyuk, and the British Interplanetary Society, to say nothing of later writers. But it reached Langley's Rendezvous Subcommittee via a brief paper written by William Michael, just a week after the Rendezvous Conference at Langley had adjourned. Michael was part of a small group in the Theoretical Mechanics Division that had been working on trajectories for lunar and planetary missions. The group outlined some of the findings in a pamphlet that made the local rounds near the end of May 1960. Michael's contribution was a brief calculation of the amount of weight that might be saved in a lunar landing mission by parking the returning propulsion and part of the spacecraft in lunar orbit. The idea hit John C. Hobart, chairman of the Subcommittee on Rendezvous, like a revealed truth or a eureka moment. He is quoted as saying,
"I can still remember the back of the envelope type of calculations I made to check that the scheme resulted in a very substantial savings in Earth boost requirements. Almost spontaneously, it became clear that lunar orbit rendezvous offered a chain reaction simplification on all back effects, development, testing, manufacturing, erection, countdown, flight operations, etc. all would be simplified. The thought struck my mind, this is fantastic. If there is any idea we have to push, it is this one. I vowed to dedicate myself to the task."
And that's exactly what he did. Hubble and some of his like-minded colleagues embarked on a crusade to convert the rest of NASA to the truth that lunar orbit rendezvous was the quickest and cheapest road to the moon. Rendezvous found an important ally in NASA headquarters when Robert C. Siemens, Jr. arrived in Washington to fill the post of Associate Administrator. Siemens, whose formal appointment dated from September 1st, came to NASA from the Radio Corporation of America, RCA, where he had been Chief Engineer of the Missile Electronics and Controls Division in Burlington, Massachusetts. Siemens' division had been one of the two Air Force contractors to study requirements for an unmanned satellite interceptor called SAINT during 1959. In 1960, when SAINT moved from study to development, RCA got the Air Force contract to develop its final stage and inspection payload and to demonstrate its rendezvous and inspection capability. So, by the end of 1960, NASA headquarters had been exposed to the idea of orbital operations and to the potential value of rendezvous techniques in manned space missions other than those related to space stations. Headquarters had also been introduced to the case for lunar orbit rendezvous as a basis for manned flight to the moon. These ideas had worked their way up from the field, chiefly from the von Braun group at Marshall and Hobart and his colleagues at Langley. The once unchallenged assumption that a lunar mission, if it were to be undertaken, would be launched directly from Earth's surface had now been called into question, and the questions multiplied in the following months. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.